Hello, Professor Christopoulos. This is Group 6. Today we are going to introduce our design of steel office building with seismic force resisting system located in Vancouver, BC. Two types of SFRS will be used in XY directions. They are BRBF and MRF. Preliminary design was conducted firstly through equivalent static force method. 5 key results will be introduced next, covering the whole process. According to NBCC 2015, the design spectrum was calculated and plotted in the diagram here, which will be used to interpolate the acceleration in terms of fundamental periods. The values of RD/R0 were selected from NBCC 2015 in terms of their ductility. The fundamental period were taken as 1.2 seconds for BRBF and 1.4 seconds for MRF. The minimum design base shears were calculated, which satisfy both upper and lower limits for base shear requirements. Lateral forces were distributed along the building height using equivalent static force method. Notional loads were also added to each story to account for initial imperfections. It should be noticed that the story shears in MRF system was amplified by U2 while BRBF system was not. In the BRBF design, brace members take all lateral forces. Beams and columns continue to carry loads induced by brace probable forces and gravity loads after brace yields. Both tension and compression forces in the brace members are shown in the second graph. Beam and column sizes are determined from interaction between axial forces and bending moments, and they are presented on the right. In the MRF design, the weak beam strong column approach was used. Beams yield first, forming plastic hinges located 500 mm away from column face. The plastic section modulus was reduced by 35% at reduced beam section, and beam probable moment acting on the column was calculated. Considering all the load effects, beam and column sizes were selected and showed in the right figure. In order to satisfy the service limit state, story drift was calculated for MRF system. It was assumed that the lateral force was reduced by 20% with an additional factor to account for the accidental torsional effect. Other story drifts were designed to be under 2.5% of the story height.
So after preliminary design, detailed design was conducted using ETAPS. The 3D model and the defined response spectrum for the given site are shown here. The braces in BRBF and all beams except those in MRF were modeled as pin-connected. All nodes within one floor were connected by a rigid diaphragm. We also designed and assigned gravity frames for more realistic structural behaviors. The translational mass in the x and y-axis and the rotational mass about the z-axis were assigned to the center of each level. However, we shifted the centers of mass when performing the RSA to account for the accidental torsion effect, assuming there is no torsional irregularity. These are the resulting scaling factors for strength and deflection. Since the structure has structural irregularities which will be introduced later, 1.0 V, the equivalent static base shear, was calculated in the left table and was used to find the scaling factors. Because the upper limit of period is different for strength and deflection, it is possible to get different scaling factors for strength and drifts, just as what we got for MRF. By observation, type 2, 3, 4, 5, 8, and 9 irregularities do not apply to our structure. For type 1, vertical stiffness irregularity, shear and flexural lateral stiffness properties were considered separately. Based on the underlined values in both tables, the structure exhibits type 1 irregularity in both directions. For type 6, weak story irregularity, the results are shown in this table, indicating no type 6 irregularity. And for type 7, torsional irregularity, from this table we can see that the structure is regular, which also verifies the assumption that we had made for the model. These are the calculations for stability coefficients and story drifts, indicating that the drift requirements are all satisfied and the p-delta effects only need to be accounted for in MRF. In this project, 3 iterations have been performed to get the final results. The key design and response parameters for each iteration are summarized here. For MRF, the RBS beam sections were detailed to be more realistic, and the column sizes have changed to satisfy both ULS and SLS. And for BRBF, section sizes were reduced in each iteration, mainly due to economical consideration, while ensuring the overall structure satisfied ULS and SLS. After 3 iterations, the final member sizes of both systems were determined, as shown here. And we also designed connections for both systems. Detailed design drawings of BRBF bridge to beam and column connections at the second level are shown here. It was mainly based on the welding solution from the core brace, and the design forces in the connection were obtained by the Whitmore section approach and the case method. And these are the design drawings of MRF beam to column connections. Bolted connection was used here.
So now we're going to talk about nonlinear time history analysis. For nonlinear time history analysis of BRBF, the model is simplified to be a 2D model with a single BRBF. This is to shorten the analysis time. The load pattern is applied as shown on the left. Mass sources are applied as additional mass at top of columns at each floor. The linear column is modeled to account the story loads which are not acting directly on BRBFs or the MRFs. In ETAPS, the linear column is connected to BRBF by assigning rigid diaphragm at each level, and the bracing members are modeled by link elements. The model is shown on the right. For BRBF, we anticipate a roughly symmetrical hysteresis in bracings. The post-yielding stiffness is assumed to be 5% of the original stiffness. A sample link element on 6th floor is shown on the right. Some key responses are shown here. It is noticed that the given ground motion one is significantly larger than the others. This could be due to scaling errors, but we didn't proceed to rescale the given data. For the same reason, the averages are calculated based on the remaining 3 ground motions. We have the accelerations, maximum interstory drift, and residual drift shown on the left. A sample hysteretic response is shown on the right. The chosen response is from the braced couple on the first floor under ground motion 3. These 2 tables summarize the numerical results we obtained from ETAPS. Comparing to our previous results from detailed design, the drifts are generally smaller than those obtained from detailed design. This may be caused by the differences between the response spectrum from NBCC and the actual response spectrum from the ground motion.
On the left side is a model of MRF built in 2D, and on the right side is rotational ductility. So when we design the hinges, we need to account for this rotational ductility on each end of the beam based on FEMA 356. The yielding moment for each section of beam can be calculated by My equals to Fy times Z, while the rotation scaling factor for beam can be calculated by theta y equals to Z times Fy Lb over 6EIB. So all these section properties are for reduced beam sections. Similar to BRBFs, the maximum transit interstory drift ratio, residual interstory drift ratio, and peak acceleration of structure at each story from 4 different individual ground motion can be found on the left figure. And it is noticed that since the ground motion 1 is off scale, we did not account for it when we found the average response for each case. And on the right figure, you can see the yielding formed in the hinges and the beams. And this is the first floor on the ground motion 2. The left table is the maximum base shear for nonlinear time history analysis, and when we calculate the average value, we only consider the ground motion 2, 3, and 4. On the right side of the table is a comparison of key design parameter for MRFs between detailed design and performance assessment. And the main reason between PA and DD may be because the different function we use. In the detailed design, we use the response spectrum, and in the performance assessment, we use the time history analysis. So this is a deformed MRF, and in our design, the acceptance criteria for drift ratio is 2.5%, and to minimize the drift ratio, we need to introduce the viscous damper.
When it comes to the viscous damper, because the 2D model we used without these dampers has already satisfied the story drift requirement, therefore the damping system being applied here is to see the influence will be brought by adding them. We have chosen the 10% damping ratio, and by following the formula of release damping, we are able to get the damping coefficient matrix. Then we took all the diagonal elements values and divide by 2, and then divide by cosine theta. And there are 2 dampers in each story, and these dampers are putting in an inclined angle. Then that is going to be the value we input into the E-tabs under the damping coefficient. After set up the viscous damper and run the analysis, here we have the comparison of the results. The results shown in the left 3 figures verify the efficiency of the designed viscous damper, which decreases the story drifts as well as the peak acceleration. The right figure shows the comparison of the hysteretic response of the hinges. It can be concluded that the damper cut down the demand and made the MRF members less prone to be yield. In this slide, the left table shows a comparison of the base shear for the structure with and without damper under different ground motion. It also shows their difference. And the right figure shows a hysteretic response of the damper at the first floor under ground motion 4. The damping force can be directly read from the E-tabs analysis result link output, because the ground motion 1 is quite off, so the mean value of the damping force is being calculated based on the ground motion 2, 3, and 4.
And that is all the presentation from Group 6. Thank you very much.